Hi everyone, I hope you all are doing well. So, today in this section, we are going to discuss a problem on reinforced concrete, cement concrete, and we are going to take a problem of simple beam section. So, let us take the example. So, we are provided with a concrete beam section of 700 mm overall depth, 300 mm is the width which is given, and it is simply supported. Having a 6-meter span, beam is loaded with 40 kN per meter of UDL. We need to find the reinforcement which is required to strengthen the tensile stresses within the beam, and to we need to draw the sketches of the same, and we need to assume the concrete to be M25 and the steel to be Fe500. Okay, so let's start this problem. So we are provided with the overall depth of the beam, which is 700 mm, width is 300 mm, and the clear span of the beam is 6 meters. Okay, and the live load which is given to us, it is a UDL, so it is given as 40 kilonewton per meter. Okay, now here M25 is the concrete, so we have FCK 25 newton per mm square, and Fe 500 steel we are using, which is having the yield stress of 500 newton per mm square. Okay, so this is the characteristic values for concrete as well as steel. So what we need to find, the area of the reinforcement, so which is represented by AST. Okay, so I hope the problem is now clear. So I have drawn a diagram for this problem. So since the beam is supported, simply supported, so let us take these are the two supports on which the beam is resting. So this is the overall depth of the beam section. Okay, so this is your front view of the section. So this is the overall depth of the beam, that is capital D 700 mm, and this is the width of the beam which is provided to us. Okay, this is 300 mm. This is given. Now this is given to us, and also we are provided with a span of 6 meters. So this is your clear span, it is not the effective span which is given to us. So what is the clear span? Clear span is the clear distance between the center of the supports. So here in this problem we are not provided with the width of the supports. First thing we need to note down, and second thing, we are provided with the span which is clear span, not effective span. Okay, so now moving forward, so here you can see what is the first thing we need to calculate. The first thing is we need to calculate the factored load for the given beam section. Okay, so what will be the factored load? So factored load will be your partial safety factor multiply by dead load plus live load. What is the dead load? Dead load will be so this is the beam section I have drawn here. Okay, so this is your 300 mm, this is the width of the beam, and this is your overall depth of the beam. Okay, now what will be your dead load? Dead load will be due to this whole section, concrete section, so we need to calculate this. So length, what is the width? That is 0.3 into depth 0.7 in meters into the density of the concrete, which is 25,000 newton per meter cube. This is the your density of the density of RCC. Okay, now what is so this is the way how we are going to calculate the dead weight of this beam section, concrete beam section. Okay, so what is the live load? Live load is given to you as 4 kilonewton per meter. Okay, so we'll convert that into newton per meter, so it will be 40,000 newton per meter. So we'll do this calculation work, and we'll get to know that what is the factored load. Factored load is coming we have calculated here 67.87 kilonewton per meter. Okay, so this is the factored load. Now second one, we need to calculate the factored bending moment due to this load. Okay, so what will be the factored bending moment? It will be WL square by 8. Okay, so what is W? W is the factored load, and what is L? Now L here is the effective length. Okay, so we need to calculate first of all the effective length of the beam. Okay, so and one more thing, we are not provided with the clear cover here in the in this numerical problem. So we all know that what is a clear cover. Clear cover is the extra cover that we provide to the reinforcement. Okay, so that it does not get corroded. So if it is the beam section, and here are the reinforcement that we are using, so this is the clear cover that we are providing. Okay, so this from here to the end point, this is called your clear cover. Okay, this is not provided. If it is not provided, then we need to assume the clear cover for our problem. Okay, so let us take the die of the bar, and that we will use, it will be 20 mm, and suppose the clear cover is 25 mm, that we are just assuming for the beam 25 mm. So effective depth will be equal to your overall depth minus the clear cover that we have provided minus the uh, diameter of the bar that we have assumed divided by 2, half the diameter. Okay, so if you can see here, if this is your overall depth of the section, this is the overall depth. From this overall depth, what we are subtracting, we are subtracting the clear cover. Clear cover is the from the bottom of the reinforcement to the end of the beam section. Okay, so this is the clear cover. We are subtracting from here this overall depth, and also we are subtracting half the diameter of the bar. Okay, so this is the diameter of the bar, half the diameter of the bar. So this is what we call the effective depth. Okay, effective depth is the depth from the top of the section to the center of the reinforcement. Okay, tensile reinforcement that we are going to give in this problem. Okay, so effective depth will be equal to your 665 mm here in this case. Now we need to calculate the effective span. Okay, our code specifies that the effective span shall be minimum of center to center of the support, or clear span plus effective depth. Okay, so we have calculated effective depth as 665 mm, and here I'll show you. We'll calculate center to center of the support first. Okay, so center to center of the support, this is the first support, this is second support. We need to calculate the center to center distance. So we are not provided here with the depth width of the supports here. Okay, so what we need to do, first of all, we need to assume the width of these two supports. Okay, so these values are also recommended by IS code. Okay, so here for instance, let us take the width of these two supports as 300 mm each. Okay, so now center to center of the support, this is a very easy task that we can calculate. So it will be equal to a clear span plus half the bearing. This is also called as bearing. So half the bearing from this side, half the bearing from this side. Okay, so we can calculate that, and it will come out to be 300 center to center is 6 plus 0.3 divided by 2 plus 0.3 divided by 2, or it will be 6.3 meters. Okay, so this is the first thing that we have checked. Now we'll check the second thing, and that clear span plus effective depth. So clear span, it is 6 meters, and effective depth is 0.665 meter. So we'll calculate that, and it is coming out as 6.665 meter. Okay, so we need to take the minimum of two values. So here the minimum value is 6.3 meter. So this is the procedure of calculating the effective span. In every case, in every numerical problem, you are going to calculate the effective span like this. Okay, so now hence the minimum of the two we will take as effective span. This is 6.3 meters. So now we'll calculate the bending moment. So bending moment will be WL square by 8. It will be 67.87 divided by 8 multiplied by 6.3 whole square. Okay, so this is the value. Now this bending moment is represented by mu. Here I have written. So mu is, this is the factored bending moment, because we have already calculated the factored load. So this is the bending moment, and it is coming out to be 336.72 into 10 to the power 6 Newton mm. Okay, so this is the second step that we have done right now. Now here comes the third step. So we need to calculate the limiting moment for the beam section here right now. So what is the limiting moment? So limiting moment, I'll explain it to you here. So if we have a beam section here, I'll draw the cross section of this beam. Okay, this is having some width b and effective depth as small d. Okay, so if we are using Fe steel and FCK concrete to build this cross section, then what will be the limiting moment that is given by this section? Okay, so limiting moment is the moment which is given by the section when its neutral axis lies at the center. Okay, at the neutral axis is just at the center of the gravity of the section. Okay, so this is the standard value, that is limiting moment of resistance. Okay, so limiting moment of resistance varies for different steel. Okay, mu limiting, it is represented by mu limiting like this, and its value is dependent upon the steel that we are going to use in the to build this cross section. Okay, so here in this numerical problem we are going to calculate limiting moment of resistance for your Fe 500 steel. So if you'll go through the basic formulas for RCCs, then you will find that a limiting moment of resistance for Fe 500 is equal to 0.133 FCK BD square. So here for reference I have written the formulas for other steel also. Fe for Fe 250, that is mild steel, we use 0.148 FCK BD square, and for Fe 415 we use 0.138 FCK BD square, and for Fe 500, that is the steel that we are using in this problem, we use 0.133 FCK BD square. What is FCK? FCK is the concrete that we are going to use. Okay, so in nutshell, if we talk about the limiting moment, then what is limiting moment? Limiting moment is the moment which is offered by the section for particular steel and for the particular concrete. Okay, so when the neutral axis just passes through the center. Okay, so now we'll calculate the value, that is mu limiting. So mu limiting here 0.133, 25 is the FCK, 300B and 665 is your D. We are taking it in mm. So we'll take mu limiting as 441.11 into 10 raised to power 6 Newton mm. So mu limiting here coming is 441 into 10 raised to power 6 Newton mm, and the moment that we have calculated for the section, it was a 336.72 into 10 raised to power 6 Newton mm. Okay, so now we'll calculate, we'll just do a check. We'll calculate the value of moment with the limiting moment. So we can find, we can see here that mu is less than mu limiting. Okay, so this section will be designed as under reinforced section. Okay, so first of all we need to calculate whether the section is going to be under reinforced, over reinforced, or balanced section. Okay, so since it depends upon problem to problem, since in the given problem we need to calculate the area of the steel. Okay, we need to calculate the area of the steel. For this we need to first of all find that whether our section is under reinforced or it is over reinforced. So obviously we are not going to use over reinforced section. So if the section comes out to be over reinforced, we'll design it as a balance section. Okay, but here we see that mu is coming less than mu limiting, so hence this section is an under reinforced section. So now in the step number 4 we are going to calculate the steel which is required. So since this section is under reinforced, then steel will fail first. Okay, so this is desired, also desired, because if steel will fail first, then it will give warning to us. Okay, so limit state says that before impending failure it is going to give you the what it is going to give you some warning before failure, and it will only happen if steel will fail first. But if the concrete fail first, then it will suddenly, the structure will suddenly collapse, which is not desirable. So hence we always try to design our RCC structure as under reinforced. Okay, so now we'll calculate mu. Since steel will fail first, so mu will be 0.87 FYEST d minus 0.42 XU. This is the formula for mu. Okay, for under reinforced section. Now we'll put the value here. What is this? This is your lever arm, this is the area of the steel, and this is your 0.87 FY. This is the, what is this? This is the characteristic value of the steel. Okay, so that is Fy, that is 0.87 Fy. When we divide Fy from 1.15, what is 1.15? Is the partial safety factor for steel. Okay, so now that is mu equal to 0.87 FYSTD 1 minus 0.42 XU over D. We are provided with mu, we have Fy, we need to calculate ST, and we have D, but we don't have XU. Okay, what is XU? XU is the depth of the neutral axis. Okay, we need to calculate that first, since this is a under reinforced section. So if this is your XU max. Okay, this is XU max, and our XU will be less than this. Okay, for this section. Okay, that is 300 mm width and 665 effective depth. Okay, for this section our XU will be less than XU max. Okay, so we need to calculate this XU first. So how will we calculate this XU in this problem? So XU can be calculated by using mu as 0.36 FCK XU d minus 0.42 of XU. This is the equation that we can use. So this equation, when you will solve this equation, this will give you a quadratic equation. We have everything that we know. We have everything in this equation except XU, so we can calculate XU from here. So this will result into a quadratic equation. So this formula is very much important to calculate XU. You can directly use this this formula, this equation, to calculate the value of XU instead of solving the quadratic equation. Or either you can solve the quadratic equation in your calculator also. So this is the formula, that is XU 1.2 1 minus 4.62 mu over FCK BT square into D. So this is the solution for this equation, the quadratic equation that will result from this. Okay, so this is the solution for that. Now secondly, we'll put this value XU value in this. Okay, and we can find the value of EST. Okay, this is the first method. Or alternatively, what we can do, we can put the value of XU over D in equation number 1. This is equation number 1. We can put the value of XU over D in the equation. So what is your XU over D? XU over D is 0.87 FYST upon 0.36 FCK BD. Okay, how this equation comes when we calculate C equal to T. Okay, what is C? C is the compressive force. Compressive force is your 0.36 FCK XU into B. okay, and it is equal to 0.87 FYAST. This is your tensile force, this is the compressive force. So to maintain the equilibrium, these two forces will be should be equal. So from here you can calculate XU over D equal to 0.87 FYAST over 0.36 FCK into B. This will give you again a quadratic equation. Okay, so the quadratic equation will be in terms of AST. Okay, how? When you will put this XU over D in this equation number 1, then it will result into a quadratic equation, and the solution for that quadratic equation is AST 0.5 FCK over FY 1 minus 4.6 MU over FCK BD square into B into D. Okay, so just remember here, this is the effective depth and this is your width of the section that is given to you. So from either of the formulas you can calculate the value of AST. So here we are using this formula, that is AST. This formula we are using 0.5. We will put the values 0.5 FCK over FY 1 minus under root of 1 minus 4.6 into 336 into 72 into 10 to the power 6. This is your MU, and this is FCK 25, and this is B, and this is D, and this is also B, this is D. So when you'll solve this, you will get AST as 1837.5 mm square. So this was the value that we were asked to calculate in the numerical problem. Okay, so or you can also calculate the value of this AST by the alternative way that I have already discussed with you. Okay, so now finally what we have calculated, we have this beam section, and we were provided with B as 300 mm, and overall depth of the beam was provided as 700 mm. Okay, we need what we were asked to calculate. We were asked to calculate the AST. So AST, as we have assumed first that we are going to use 20 mm dia bar. So this is the AST. Okay, so number of bars we can calculate easily. So this is the area of the reinforcement that we have calculated. So this is your AST, and this has come out as 1837.5 mm square. Okay, so you can easily calculate the number of the bars also, number of bars if you want to calculate. So number of bar will come out to be 1837.5 divided by area of single bar. So area of single bar, as we are going to use 20 mm dia bar, so pi by 4 d square, that is 20 square. Okay, 5.85, and this value is your, these are the number of the bars, so we'll use 6 bars. Okay, so this is the 6 bars. You can also calculate the spacing between the bars also. So here in this problem we just need to calculate this area of steel that we have done here. Okay, so please go through the numerical problem again. So, and I hope you all are doing well, and thank you so much.